Today we're going to be learning about DeMoivres Theorem and Nth Roots, or as I like to refer to him, DeMoivres, because that's kind of how it's spelled, really. Let's be real here. I'm going to skip the warm-up and just go right into the first exploration, where we're going to be using the property we learned about last class, where we multiply these trig form of complex numbers. And just as a reminder, if we have a complex number, a plus bi, we can write it in trig form, which would be written, I don't want to write it that way, which would be written r cosine theta plus ri sine theta, and that we normally abbreviate this as r kiss theta, okay, as our shorthand. So we want to see what happens when we start raising these to powers, and this is when we're going to find out how powerful the trig form really is and what makes it so much better than the standard a plus bi. So if I have z squared, okay, so that's really z times z. So this is r kiss theta times r kiss theta. And according to our formula over here, that means that we can just multiply the two radiuses and then add the angles. So if we simplify that, we get r squared kiss 2 theta. So now let's see what happens if we do z to the third. Okay, so that would really be like a z squared times z. So z squared, we already figured out, that's r squared kiss 2 theta. And times an additional z would be r kiss theta. So if we just apply our property up there, that's going to be the radiuses times each other. So r to the third kiss, and then we would do 2 theta plus theta. So that would be 2 theta plus theta, and we could simplify that, r to the third kiss 3 theta. Have you figured out a pattern yet? What's it going to be for z to the fourth? Shout it out. Ah, perfect. You're totally right. It's r to the fourth kiss 4 theta. How about z to the fifth? Totally nailed it. R to the fifth kiss 5 theta. So we end up with z to any power in the world can be written as r to the nth power kiss n times theta. And this is DeMoivres, or DeMoivres Theorem. So let's try to see why this is so powerful. If we were given this complex number in standard form, 1 plus I squared root of 3, raised to the third power, this would be incredibly annoying to do by hand. We would have to FOIL this out once to get a quadratic, and then FOIL it again to do the third term. Using DeMoivres Theorem, though, it's significantly easier. But the first thing we need to do is get this into trig form, because DeMoivres Theorem uses trig form. So I personally find the easiest way is to just graph this complex number. So this is going over 1 and up square root of 3. So I can recognize what type of triangle this is. That's 2. This is going to be 60. Okay? So I can rewrite this inside thing as 2 kiss, and I'm going to use radians, pi over 3. So that's really what I'm being asked here. 2 kiss pi over 3 raised to the third. So now I can apply DeMoivres theorem. This is going to become 2 to the third kiss, and then I just multiply 3 times the angle. So simplifying this, I'm going to get 8 kiss. This is just going to be pi. And now since they gave us our original thing in standard form, we need to make sure that we rewrite our answer in standard form. So personally, when it's a quadrantal angle, I always find it easier to just plot it, because then I can look at this and see that this is just going to be negative 8 plus 0i. So negative 8 and then up and down 0. So this complex number raised to the third power equals negative 8. And one of the things that we're going to be exploring a little bit later on is kind of making a stronger connection between this little formula right here, z to the third equals negative 8, and what happens if we take the cube root of z, that would actually equal this original complex number up here, 1 plus I rad 3. But we know from the fundamental theorem of algebra that something raised to the third power actually has 3 different answers. So what are the other 2 answers? And that's the second half of today's lesson that we'll be trying to figure out. For example 2, we have this complex number here raised to the 8th power. So this would be really not impossible, but it would be very difficult to do in standard form. We would end up having to FOIL pairs of these probably 4 times, and then we'd have to take those 4 and combine those, and take that one and combine that, and it would be very difficult to do. Trig form, very easy to do actually. First thing we need to do is just figure out what is this in standard position. So I'm going negative and up, so that's going right here. I recognize this as being a 45, 45, 90 triangle, so that's a radius of 1, and that's 45 right there is a reference angle. So this inside thing, it has a radius of 1, and then an angle of 3 pi over 4. So that's really what's being raised to the 8th power here. And now if I just apply DeMoivres Theorem, I'm going to get 1 to the 8th power, kiss 8 times 3 pi over 4. This inside here, that's going to reduce to 6 pi, which is coterminal with 0. Okay, so this is really just saying 1 kiss of 0. So if I graph this in standard form, that's an angle of 0, and it's going out 1. So it's right there. So this is actually 1 plus 0i. And again, we're going to be making this connection real soon, but what we really just found was that some complex number raised to the 8th power equals 1, which means that we can work backwards and say that the 8th root of 1 equals that complex number. But again, if we have something to the 8th power, then that means that there are 8 actual answers. So what are the other 7 answers that we're missing here when we do the 8th root of 1? This particular complex number right here actually has a special name. It's they're referred to as Nth Roots of Unity, which is basically that we end up getting 1 after we raise them to a power. And there are a whole bunch of really neat applications that we could use with this, but the most common thing is that these roots of unity end up connecting directly to the unit circle, which has a lot of practical applications in the real world if we were to start applying these things. So the last part of this lesson is dealing with using roots of complex numbers. So here I have the nth root of the complex number z, and it equals this kind of crazy formula. But it's similar to the raising it to the power, right? We had r raised to a power. Over here we're just doing the nth root of that power. Over here we multiplied theta by n. Here we're dividing it by n, so there's similarities, but we have this extra 2 pi k up there. And I'm going to deal with that when we're doing the actual example. And I actually think it makes more sense for us to start with example 4. So I'm skipping example 3 for now, and I'm jumping to example 4, which says find the cube roots of -1. Okay, so I want to know z equals the cube root of -1, and I want to figure out what are these values. But if we write this the other way around, this is really saying z to the third equals -1. And you could actually solve this without doing a whole bunch of crazy math, probably. You could actually rewrite this and say this is really z to the third plus 1 equals 0. We could factor this using that thing that you always forget. That's, same sign, opposite sign, always positive. And we could actually figure out what the real component and the imaginary ones are. This will get more useful when we make this like an 8, and you wouldn't be able to do this algebraically. But let's start off trying to do this. The first thing we need to do is rewrite -1 as a complex number. So let's think about this. -1 is really plus 0i, so that's going to be over here. So that's going to have a radius of 1 and an angle of pi. And it's really important here that we don't use negative radiuses with a positive angle over here, that we use the actual angle with a positive radius. Okay, so that's just going to make our lives much easier if r is positive and theta is positive. I actually believe by definition that's the way this works, so it kind of has to be that way. So now that we have that, what we're going to do is plug things into this formula up here. So I'm being asked to do the cube root, so I'm going to do the cube root of the radius, which is 1. Okay, then I'm going to have kiss the angle, which is pi, plus 2 pi k, I don't know what that is yet, divided by, and then I'm going to have a 3 here because that's the root that I'm doing. So let's figure out what to do with this k now. And it has to do with how many roots and how many answers we have. If we have z to the third, then we know that there are 3 answers. So this k is going to be how we find the 3 different answers, by letting k start off at 0, and then figuring out what it is at 1, and then figuring out what it is at 2. And notice we actually stop here at 2 because we have the 3 different answers we want. Here we have this nice little grid going on here. I'm just going to basically evaluate this for each one of these k values. And I like to do it kind of in pieces because certain things don't change. So for example, the radius doesn't change. What's the cube root of 1? It's always 1. So all of these have 1. Then they're all going to have kiss. Next, we'll have pi plus 2 pi, k is 0 for the first one. So this whole term is now gone. So I just have pi over 3. Now if k equals 1 for the next one, I'm going to have pi plus 2 pi. That's 3 pi over 3. So that's just pi. And then if k equals 2, this is going to be 4, and plus the 1 there, this will be 5 pi over 3. And now I can just convert these back into standard form because these are special angles, so we can rewrite them. So let's think about this. This really is cosine plus I sine of this angle. So cosine of a pi over 3 is going to be 1/2. Sine of pi over 3 is a square root of 3 over 2. Do the same thing here. Cosine of pi is -1. Sine of pi is 0. Okay, so that was one that we already knew about, right? We know that the cube root of -1 is going to equal -1. Do the same thing down here. Cosine of 5 pi over 3, that's positive 1/2. Sine of 5 pi over 3, that's going to be a negative square root of 3 over 2. So these are the answers. These are the cube roots of -1. All 3 different answers, including the imaginary and the real that we already knew about. So I hope you're kind of getting the idea of what makes this trig form really important and why we're bothering to teach it to you. It makes us actually satisfy the fundamental theorem of algebra much easier when we're dealing with something like z to the 3rd. And if we change this to a z to the 8th, well, all we would have to do then is just have the k value go all the way up to 7. We start at 0, so we don't have to go all the way to 8. And then just increase it, and we would find all 8 different answers if this had been z to the 8th equals -1. That would be virtually impossible for us to do algebraically with traditional algebra like you're used to. So it's a very neat property. Let's jump back and do example 3 now. That we've done example 4. We're going to have some z value equals 5 kiss pi over 3. And we're being asked to find what the 4th roots of this are. So we want to know what the 4th roots of z are. So the first thing I'm going to do is just plug it into this formula. So I'll have the 4th root of 5, kiss. Theta is pi over 3, and then plus 2 pi k, all over 4, because I'm doing the 4th root. Now, right here, what I like to do is simplify this before I start plugging in any k values. So when I do that, I'm going to end up with a pi over 12. So I'm just going to write that over here and not rewrite the whole thing. So pi over 3 divided by 4 is going to be pi over 12. Plus, this would be a 2 pi over 4. But it's really nice if we actually leave it with the same base over here, okay? So what I'm going to do is actually write this as plus 6 pi over 12k. And you'll see why that's useful when we start plugging in the values. But essentially, we're just going to be able to add 6 each time we increase the k value, because over here, that's just going to be a multiple of 6 when we have the same denominator. So let's jump over here. We'll do k equals 0, k equals 1, k equals 2. That was the straightest line ever. And k equals 3. We don't need to go past 3 because we have the 4 answers that we're looking for. They all have this 4th root of 5, so I'm just going to start off by writing that for all of them. That way I don't have to think about it. They all have kiss next, so I'll just write kiss next. And then they'll all have an open parentheses. So now let's start with the first one, and I'm going to use this over here. When k equals 0, I just get pi over 12. Done. When k equals 1, I'm just going to be adding an extra 6. So if I add 6, that's going to become 7 pi over 12. And then I'll just add 6 again, so that's 13 pi over 12. Add 6 again, that's 19 pi over 12. Okay, and that's all because we were able to simplify this to get this common denominator, which basically says every time k increases, we're just adding 6 pi to the top. And since these are not special angles, we leave them, and these are our final answers. So these are the 4th roots of this complex number 5 kiss pi over 3. So for practice 1, they want us to take 1 minus I rad 3 squared and use the foiling method, so that's the old school way. So let's just write that out so that we can actually do the FOIL method. So I'm going to do 1 times 1, that's 1. I'm going to have minus I rad 3, minus I rad 3, and then I'm going to have plus I squared, square root of 3 times square root of 3, that's going to be 3. So I probably should have written that the other way around, but oh well. This right here, I squared, is really -1. So I really have a -1 times 3. So that's -3 plus this 1 right here. So I have -2. And then these are like terms. So I have -2i rad 3. So that was using the FOIL method. 2 wants us to use DeMoivres Theorem over here. So the first thing that we need to do is actually convert this into trig form. Okay, so I personally find the easiest way is to graph this so I can recognize the triangle. I do, it's got a radius of 2. This was an arrow, it looked like a 2, sorry. That was a 60, okay, but I'm going to use positive angles when I do this stuff, so I'm going to say that this is really equal to 2 kiss, that's 5 pi over 3, and I'm raising that to the second power. Following the formula here, I'm just going to do 2 squared kiss, 2 times 5 pi over 3. And let's see, what does this give us? That's 4 kiss, and this ends up being 10 pi over 3. And 10 pi over 3, that's coterminal for, let's see, 6 pi, so 4 pi over 3. Okay? So I want to convert this out, and there's a couple different ways that we could do this. We could just do what is cosine of 4 pi over 3. It's a -1/2, so I'm going to have the radius times cosine 4 pi over 3, plus the radius times sine of 4 pi over 3, so it's a negative square root of 3 over 2i. You could also, if you wanted to, plot this angle, which is over here, with a radius of 4, and then complete the triangle to get the 1/2 and get the numbers that we'd actually get here. So I'm going to end up with -2, and then minus a 2 rad 3 times the I value, and that is the exact same thing that we got up there. So this way looks like it's a lot more work, but we only are squaring here. What example 3 and 4 are going to be doing is showing us, well, what happens when we have powers bigger than 2. It's going to be significantly easier for us to just convert it into trig form than it is to do the foiling method. So let's do that for example 3. We have this, so I'm just going to rewrite it out because that's easier for me to be able to see what I'm trying to FOIL. I'm going to start with these things right here. So I'm going to have -1 times -1, that's +1. -1 times -i is going to be +i, and I'm going to get 2 of those, so I'm going to have +2i. And then I'm going to have a negative I squared, so that's going to end up being that. Let's simplify this a little bit more here. This ends up being -1. So 1 times one plus -1 is 0, so I'm really left with just 2i times the -1 minus I, and this actually made our lives much easier. If that had been 2 terms, we would have had to FOIL again. Here we just have to distribute. So I'm going to do that over here. -2i minus 2i squared. Again, that's really -1, so this ends up being 2 minus 2i. Let's do the exact same thing now, but using DeMoivres Theorem over here. So first thing I'm going to do is try to rewrite this in trig form. So a -1, that's going to be down here, -1, -1. I need to figure out what the radius would be. So the radius is actually going to be the square root of 2, and that's a 45. So I'm doing square root of 2 kiss 5 pi over 4, and that's what I'm raising to the third power here. So let's figure this out. This is going to be square root of 2 to the third power. Yes, we could rewrite that. We will in a little bit here. Kiss 3 times 5 pi over 4. So this is going to end up as 15 pi over 4, which is coterminal to 7 pi over 4. So I just did that. A 16 pi over 4 would have been back at 2 pi, so this was 1 less than that, so 7 pi over 4. So let's evaluate this now. A square root of 2 to the third power. Cosine of a 7 pi over 4, that's going to be a positive square root of 2 over 2, plus square root of 2, 3i. Sine of this is going to be a negative square root of 2 over 2. So now we have to do a little bit of math here that probably been a while since you've done, but if I do square root of 2 to the third times an extra square root of 2, that's going to be the square root of 2 to the fourth over 2. Okay, square root of 2 to the fourth, that's actually just 4 over 2, which is just going to end up equaling 2, but I'll get there. We get the same exact thing over here. I get the square root of 2 to the fourth over 2i. So again, that's going to be plus, sorry, there's the negative sign there. I missed that. Negative negative 4 over 2i. So if we just simplify that, we're going to get 2 minus 2i, which is the exact same thing we got up there. And again, if we were to keep going and making that a 4, this would be the same amount of work. This would now be much more work. If that was a 5, 6, 7, 8, 9, or a 10, this would be a lot of work. Here we would have the same amount of work in order to, like that same amount of work that's right here. Whereas this one would have, 10 times the amount of work. Example 5 wants us to find the 8th roots of unity. So basically we want to know that word unity means 1 plus 0i. So what we're being asked to find is what are the 8th roots of 1. So the first thing I need to do is put this into trig form. So 0 plus 1i, that's going to have a radius of 1 and an angle of 0. So that was actually pretty easy to do. Now I just follow the formula. I'm going to do the 8th root of 1, kiss, 0 plus 2 pi k all over 8. And if I just simplify this inside part here, this ends up just being, what is that? Not 4 on top. A pi over 4k is the inside. So then I have to do 8 million of these k equals 0, 1, 2, etc., etc. I have to go all the way up until I have 8 of them, which is going to be at k equals 7, because I started at 0. Oh boy, so much. I'm going to run out of room. Oh my goodness. Whew. All right. So what is the 8th root of 1? You're totally right, it's 1. So all of these have 1 kiss to start off with, so I will just write that because I think that's significantly easier to do than having to rewrite it every single time. Next, I'm doing basically multiples of pi over 4. So I'm going to have 0, when k equals 0, I'm going to have pi over 4. When it's that, I'm going to have pi over 2. Then I will have 3 pi over 4, 4 pi over 4, so just pi, 5 pi over 4, 6 pi over 4, which is 3 pi over 2, and then last but not least, 7 pi over 4. And I'm realizing my answer key has that one as 7 pi over 2. It's definitely a 4 though. All of these are special angles, which means I need to rewrite them back in standard form. And I personally think it's way easier to try to visualize what's going on here, particularly on like the unit circle side of things. So I'm going to get this one right here, which is going to be 1 plus 0i. Let's jump to pi over 2. That's going to be up here. That will be 0 plus 1i. If we do pi, that's right here, so that's going to be negative 1 plus 0i. If we do 3 pi over 2, that's down here. That's going to be 0 minus I. Then we have all of the pi over 4s. So they're all going to have x and y values, or a's and b values, of square root of 2 over 2, but just the signs are going to change. So I'm going to have square root of 2 over 2 plus square root of 2 over 2i. Here, the x values, or the a values, are negative when we're in this quadrant. So it's negative square root of 2 over 2 plus positive square root of 2 over 2i. In quadrant 3, they're both negative, so square root of 2 minus square root of 2 over square root of 2i. And down here, x is positive, but y is negative, so a is positive, square root of 2 over 2, and b is negative. So these are all 8 answers for the 8th root of 1.